Okay, we've seen that the drag force is proportional to v squared. Our equation mv prime becomes mv prime equals f minus cv squared, and this is a general solution provided v is less than the square root of f over c. V less than the square root of f over c ensures that this denominator be positive, so that we were justified previously in removing our absolute value signs. Now, we solve this equation for v, and without going into all the gory details of this, let's just solve an equation of the form 1 plus av over 1 minus av equals capital B. We see that if we multiply both sides of the equation by the denominator, we get 1 plus av equals b multiplied by 1 minus av, which is 1 plus av equals b minus b times av, and bringing the v terms over in one side, we end up with b times av plus av equals b minus 1. Factoring the v out of both sides, we have v, and we'll factor out the a as well. And then that's multiplied by b plus 1 equals b minus 1, so that v equals 1 over a multiplied by b minus 1 over b plus 1. Now, applied to this equation, a is going to be the square root of c over f, so that 1 over a is going to become the square root of f over c. Our b is just our a e to the 2 square root of fc over m multiplied by t, so that the equation will actually come out in the form v equals the square root of f over c multiplied by b minus 1, that would be a e to the 2 square root of f c over m t minus 1 divided by a e to the 2 square root of f c over m t, and I'm writing that small and not very neatly because it's not really necessary to see all those details. But the thing I'm going to do to this to get down to this form is I'm simply going to divide both numerator and denominator by e to the 2 square root of fc over m, and that's going to make this term 1, and this term, when divided by this exponent, is going to become e to the negative 2 times the square root of fc over mt. So by fairly straightforward rearrangement, it's not dissimilar to rearrangements we've done with solutions to other equations. Our equation ends up in this form. Now, let's go back for just a minute and consider the equilibrium solution of this equation. What's going to be necessary for equilibrium? Well, clearly this equation is going to be in equilibrium when v prime equals 0, which is going to occur when f minus cv squared equals 0, and that occurs when f equals cv squared, which occurs when v equals the square root of f over c. Okay, this is the equilibrium condition, the condition in which the velocity will be unchanging. As a result, we interpret this term as our terminal velocity, the velocity that we expect our solution to approach as t approaches infinity, so that when put into this form, our solution has the terminal velocity out here in front and these terms over here. Now, I'm not going to write that yet as terminal velocity, but we will shortly. Let's consider a special case here where we start from rest. So the initial velocity is, well, actually we're not starting from rest. V naught is, V of 0 is V naught. We have an initial velocity which might or might not be 0. And we'll see what happens when the initial velocity is 0. We get a kind of an interesting solution in that case. So if V of 0 equals V naught, then this expression here, where we plug 0 in for t, our velocity function then becomes square root of f over c multiplied by a minus e to the 0. Well, e to the 0 is 1, so we get a minus 1 for the numerator, a plus 1 for the denominator. And our condition v of 0 equals v0 becomes this, an equation that we can easily enough solve for a. Now, the technique we use in solving for a is very similar, almost identical to the technique we used in solving this equation, so I'm not going to go through the details of that. But I will observe that our solution, which is a plus the square root of c over f v naught divided by 1 minus the square root of c over f v naught, becomes, if we keep in mind that our terminal velocity is the square root of f over c, then the square root of c over f is the reciprocal of the terminal velocity, and our solution for a becomes 1 plus v naught over terminal velocity divided by 1 minus v naught over terminal velocity. This could be written in the form 1 plus r over 1 minus r, where r is the ratio of initial velocity to terminal velocity. Now, that is, r could be understood as the fraction of the terminal velocity that's initially present. That is, r is initial velocity as a fraction of terminal velocity. So if the initial velocity was 1/10 the terminal velocity, we would have a equal to 1 plus 1/10 divided by 1 minus 1/10. Now, if the initial velocity is 0, it's very easy to see that a becomes 1. Okay, either in this form or even in this form. These terms are going to be 0. We're going to get a equals 1 over 1. Or these terms, or the r's, will both be 0. We're going to explore the solution for the case where v naught equals 0.